Live from the Orion Cygnus arm of the Milky Way galaxy, this is Scientifically Speaking, a weekly half-hour program devoted to elegant curiosities, and I am one of your hosts, Sarah Chang, and joining me, as always, in always bright spirits, is Bernie Ryan, BJ Star Watcher. How are you, Bernie?
Yes, hi, Sarah. Very good. Thank you.
Bernie is our professor of the astronomy lab at USM and protector of our local night skies here in Maine. Reach out to us at WMPG Scientifically Speaking at gmail.com or Twitter at WMPG SciSpeak. Feel free to DM me or tweet at me if any questions, and we will try and answer those on a specifically curated show. All right, Bernie, could you
Yes.
let our listeners know what is up in the night sky for this coming week?
Okay, yes. Well, this week will be Friday the 27th. So we're going to have a waxing gibbous moon. So we'll be able to see that. It's going to set before midnight. But the main thing to be looking for will be the total lunar eclipse once the moon gets full. We will have a lunar eclipse. Actually, it won't be total. It's what's going to be called a partial penumbral lunar eclipse. So it'll be about 83% covered by the shadow of the Earth, but that should be enough to notice it. I mean, you may want to try to photograph it or have a pair of binoculars, but even just looking at it, you should notice it. The problem is, since it won't be total, it won't go completely red. It won't get really dark and stuff in the sky, and the moon won't go red, and you won't see the whole thing going through the middle part of our shadow, but you'll see it go through the penumbral part of the Earth's shadow. The only problem is the timing. It's not really going to be starting to be visible till about 4:30 in the morning. It's going to peak at 4:45. So, of course, if you like getting up early, that's no problem, or you could just stay up or whatever. And that's going to happen Monday, November 30th, when it hits full moon in a few more days. So you should look for that. But other than that, just keep watching the same thing. Jupiter and Saturn are getting closer and closer together. They're probably just maybe 3 or 4 degrees apart now. They're going to be less than a tenth of a degree apart on the first day of winter, December 21st, so less than a month from now. And that's the closest in 400 years. But I just read today, observably, the last time that was really seen and recorded, I guess it happened and maybe we know it was in the morning, is 800 years ago. So for
Oh, wow.
seeing them this close, so 800 years, the year 1226. So just keep watching all that unfolding, and obviously we'll talk a lot more about that before the actual winter solstice and that happens. Other than that, Mars is still nice and bright. It's already fairly high by the time the sun sets. You can still see nice features in the telescope pretty much through the whole month of December. So another month is only a month past its best. And then Venus comes up a little later in the morning. It's probably up by 4:30 now. And then Mercury can be seen a little bit next. Yeah, Mercury can still be seen. It'll be about visible in the morning for about another week. So basically, we can see all five of the planets.
That's awesome. Don't we have an eclipse coming up, a solar eclipse?
Oh, yeah, yes, of
Or
course. See, once we go into eclipse season, a lunar is always followed or preceded by a solar. So the solar will be December 14th, and we can talk about it more next week. Unfortunately, it won't be for us. We won't even see
yeah.
a partial. But it'll have almost the same path that the one they had July 2nd of last summer.
Oh,
Uh,
nice.
it covers two countries, Chile and Argentina. So the shadow will race across in just a few minutes. It took 90 minutes to race across the whole country for the one we saw. And it's only 600 miles south of where the other one was. So it'll cover where some of the big telescopes are. And that's December 14th, probably around 11 in the morning, similar to the timing that we had. So, yeah, but far fewer people, I'm sure, are going to travel. Even people that were probably already booked to travel may not feel safe to travel in only like not even, a couple weeks from now. Yeah, right.
Yeah, yeah,
So, but there are ways to watch it, and I'll mention it later. You can watch it on the San Francisco Exploratorium. There's a really good live website. They send live people down there. Somebody, I guess, has to travel there. And then slew.com, which is a site run by an English astronomer. They run the big telescope remotely in the Canary Islands. And then there's some other really good sites, and then individuals that can just set up a feed like on YouTube. But those are the big ones that'll have professionals, and they'll have other interesting people they talk to, because the event, it's only going to be 2 minutes and 8 seconds. It's going to be less than what we saw. We saw like 2 minutes and 20 seconds. But it's a 3.5 hour event. They'll carry it live, and they'll have a lot of interesting people going the whole time. And you'll learn a lot of things other than just seeing the eclipse indirectly.
yeah. Those are always a lot of fun.
Oh, yeah. Yeah.
Sweet. Well, thanks, Bernie.
Yep. You're welcome.
And if you couldn't take notes fast enough, see how I changed
Yeah.
that?
Hmm.
You can also check out the monthly What's Up column in the Portland Press Herald. I hope, or we hope, that everyone had a great week giving thanks, and hopefully it was a safe and warm week for you guys. So, keeping the tradition alive here at WMPG 90.9, we are celebrating Black Hole Friday. I think there have been a couple of new things coming up in or that have happened in black hole kind of science news. But actually, first, before we get to that, Bernie,
Yes.
you had watched a couple of launches, right?
Yes. Yeah, these are really amazing. Actually, one of them, a student had just emailed me like an hour before, so I quickly posted to all my like 80 some students to see if they could try to watch it live. So the Dragon capsule from the Falcon 9 rocket launched four astronauts, there were three on board, four new astronauts to the ISS last week. So I
Wow.
watched it live again. It was like a 4 hour event, but you got to see all kinds of things. Of course, the launch only takes like 8 minutes to get to space. And then it took about a day and a half to get there. Then they had another live 4 hour event when they docked with the ISS and they opened everything up. And the four astronauts went in to meet the three that were already there. So that was kind of neat. I didn't watch that one for 4 hours, but I watched live. So it kind of puts you there. And again, you learn a lot of, other ancillary things. Like I've been to the Kennedy Space Center a couple times, so I knew where they were launching from and what that was like. And yeah, so it was really neat watching that. So the Dragon capsule now is a commercial space launch that basically
Wow.
means anyone can go. And you have to pay; it won't be cheap, but you don't have to train for 20 years to be an astronaut. Those four people were astronauts, but anyone can now go to space on this. I mean, it's commercially done. It's totally safe. It was done successfully 100 times. I think they had one partial failure. They like a couple of years ago. I think Seth was still on the show with us.
Yeah.
Something happened. Everyone was safe and then one other time something else happened and no humans involved.
Yeah.
100 successful launches now in the last few years. And then, so that was great. And then they launched just yesterday another Falcon 9 rocket because they are reusable rocket boosters. I
Yep.
mean, even the same one, if they could truck that out to Vanguard Air Force Base in California in that week or so. So they launched a new satellite called Sentinel-6. It's part of monitoring the oceans for climate change. So it can measure the difference in sea level of less than an inch from 800 miles up.
Wow.
The whole series of, they had Sentinel 1 through 6, and then they had the Jason satellites before that. It's going to be up there for at least 5 years, and then they'll send up a renewed version, a twin, that's going to be even more accurate. And they actually measure the entire column. Warm water actually has a higher water column than cold water.
Yeah.
Really amazing things that it can do. So they watched that launch and they talked to the experts and they interviewed the children of the person, Michael Furlick. He basically designed this whole satellite. So it's just called Sentinel-6, but it's really his work. And it's going to be up there monitoring the earth, the oceans in tremendous detail. See, the sea level is now rising 5 millimeters per year. Just a few years ago, it was only 3 millimeters, then it was just 2. So that rate is increasing. So we'll have so much more useful data. Now it can also monitor the beaches and not just the middle of the ocean. So we're going to see how all this works and collect all that in, very accurate telemetry. And then they got into all the technical details about how all that works. But just having it up there, and everyone can access it. I mean, you and I could access it. Obviously, the weathermen for news, they'll be important for them to access it.
Yeah.
We can interpret it, we can access that data too, because essentially, we paid for those satellites through our taxpayers' money, so we should have access to them. But we do. So it's really neat to see how all that works and what's out there and what we can access. Yep.
That's awesome. Thanks, Bernie.
Yeah, sure.
That's your regular rocket launch update here
Yeah.
at WMPG 90.9.
Yeah. Right.
All right. So back to the spirit of Black Hole Friday. We wanted to kind of highlight some of the work that recently, this was in October, right?
Yeah, October
Where
6th.
the 2020 Nobel Prize
Right.
winners were announced. And
Mhm.
our 2020 Nobel Prize winners
Physics.
in physics, they went to, or it went to Roger Penrose,
Mhm.
Reinhard Genzel, and Andrew Ghez.
Yep.
And I basically narrowed it down to they proved that black holes existed. But I know, Bernie, you had talked
Yeah.
about how it was really 20 years worth of work,
Yeah.
which I guess when you think about it, that's kind of a short time for
Mhm.
science because many
Yeah.
things take a very long time, like much
Yeah.
longer.
Yeah.
And so basically, Penrose had performed some calculations, mathematical calculations that showed that black holes were physically possible. and Gensel and Gez showed that these objects essentially lurk at the center of our galaxy. So I don't know if Bernie, can you take us through some more detail?
Sure. Okay. Well, it's kind of interesting because black holes were actually proposed way back in the 60s. They found the first one in Cygnus in 1971. They even took a picture of the first one in April of 2019, last year. But still, I mean, they didn't know it was actually a black hole. It could have been something that acted like one. It could have been several of them, just some region. So this was important math. I mean, Penrose was been working on this since the 60s himself. Someone named John Wheeler actually coined the term, a physicist that just passed away a few years ago.
Of black hole, you mean?
He coined the term black. Actually, I
Gotcha.
had one of his granddaughters in my astronomy class like 10 years ago.
Oh, what?
I think she was studying to be a lawyer after that, so she's probably,
Here?
yeah, right here. John Wheeler's
What?
granddaughter was in my class.
Wow.
Freeman Dyson's granddaughter in one of my classes too. And Freeman
Wow.
in his 90s, he just passed away. So yeah, so a little interesting side. But yeah, so I mean, I thought they were pretty much proven. You know, we even have a picture, but they really weren't. So they did. Roger did the theoretical side, and then the other two, Getz and Genzel, did the experimental side. So it's a nice marriage of the two, which is a nice way to give out a prize. I guess Roger did more of the heavy lifting. He got half of the $1 million, and the other two had to share the remaining $500,000. But you know, kind of beside the point because the other two really weren't expecting that. But so what Roger did through his math, and obviously I can't begin to get to the math part, but I can kind of show you in practical terms what it is. I mean, Roger obviously came from a brilliant family. His brother he teaches at Oxford now, was a 10-time national British chess champion. His father was raised as a Quaker, and I think he was also a teacher. So he has an interesting background and so on. So obviously he's very good at those aspects. Okay, so what Roger Penrose proved to actually show that black holes exist, and they're not just theoretical, even though you can get a picture of them. So what he did, he showed that all the paths of the light that will go into a black hole will point towards the singularity. So any path you take, like I mean, anything can actually be a black hole, which is kind of neat. If you can form enough pressure on anything, you could turn a person into a black hole, a cell phone, a desk, a computer. If you hit that event, the amount of space that will create the singularity, you can turn anything into a black hole. Now, in
Now, I guess the difference would be how long it lasts.
yeah, right, exactly. A small black hole, because of Hawking radiation, would disappear in a split second.
Mm.
So the monster black hole that these people were studying, that's probably going to live for trillions and trillions of years and so on. But okay, so Roger Penrose showed that the path of all the light will have to go in toward that singularity, and there's really nothing you can do about it. There's no way to avoid it, like you can't even avoid the next moment in time. So all the possible path of light will bend to that. But the neat part about it is that that's kind of in the future. It's a future point because you're talking about the flexibility of space-time, because light is always constant, but space-time is flexible. So he kind of proved that that would have to be the case, you know, regardless of all the images we've taken, you know, all the
Wait, what does that mean by space-time is flexible?
yeah, well, because light is constant. I mean, you know, you can't add or subtract from the speed of light. You can be moving at almost the speed of light, and light will still be moving at that speed. You can't add or subtract to it. That's Einstein's famous, you know, experiment on the train and his mind experiments traveling near the speed of light in the cone and how things would
Sure.
happen. So that's constant. So that would, for that equation still to work, space and time are both flexible. Now you don't normally on Earth they're flexible right here. GPS satellites wouldn't even work without that. Even
Yeah.
the difference from 12,000 miles up to here is quite a bit. Time flows differently. But what's even more interesting, time would flow differently on the ground floor of the building where I teach in versus the fourth floor of my
Right.
in Gorham. Time would even flow differently.
Yeah.
It's less than
Okay, I see what you mean.
a second, which
Yeah.
is a trillionth of a second, but we have atomic clocks that can measure this. So time flows differently, but near the black hole, it's a huge difference. Time would flow so much slower. Basically, you know, you would like, and this is like the movie Interstellar, who basically got it right. I mean, they had Kip Thorne as an advisor on it, so that helps.
That was a good movie.
McConaughey, he spent about, I don't know, like 1 hour near that event array. He didn't go in, obviously, so you don't want to do that. So his daughter on Earth aged about 7 years for every hour he spent there. So she became older than he was. So I don't know, like 4 hours later, you know, she was like 50 or 60 years older than her father, and that's all very possible. And we can do that with particles, not obviously with people. So yeah, so space-time is flexible, and this is like pure gravity. You can see all these things
Yeah.
happening, all the interactions. And that's what he proved mathematically. I have no idea the math of how he did it, but that means that it actually has to be there. It's not just, something Einstein theorized. It's not something that you get a picture of, and that's actually what's there.
Do we know how complex that proof was? Was it like 500 pages?
Oh, actually, Jen 11 said it was fairly simple.
Oh,
Oh,
really?
Penrose, I think, no, she mentioned he wrote a paper back in the 60s that was only like 3 pages long and just brilliant. And maybe he built on that. I'm sure what he did for this particular prize wasn't just a 3-page paper. Yeah, no, you're right.
Yeah, yeah.
But he really has a way to narrow that down and show what it is. But when you mention complex, I thought you were going to ask about some of the properties of a black hole, and they're actually very simple. They really only have like 3 properties, and often you can just use 2 of them to figure out what it is. So it only has mass, and then it has spin, and it would have charge. But the charge is not even necessary to really study the charge. It has mass, obviously, and at different sizes, and then it spins. And that's pretty much it. So you can prove things, a lot of things about it very easily. I mean, it takes a lot of time and detailed measurements, but
Right.
you can do it.
Yeah. Well, nice job to, I assume, Dr. Roger Penrose.
Oh yeah, I'm
Um,
sure he's almost 90 years old himself. Like
oh, wow.
Freeman Dyson was like 90 something. So yeah,
So does he teach somewhere or
I
is
think
he
he's still
just,
teaching at Oxford. I mean, he may be
okay.
doing more research, and
Okay. I
yeah,
think,
I'm
yeah.
sure he's
You
helping
mentioned
the
Oxford.
entire field by having won the Nobel Prize. Now probably lots of other people, and even the other 2. I mean, they all have grad students that are working on this.
Sure.
That they got the prize. It's going to push that whole field along even further. Yeah.
So what about Reinhard Genzel and
Hmm.
Andrea Ghez?
Okay.
What role did they have?
Yeah, well, they did the experimental part, which is very good. So, as you said, it's like 15 or 20 years of research. So, we knew first theoretically and now actually that there is a supermassive black hole at the center of our own galaxy. It has
Sagittarius A
billion
star.
solar masses. It's called Sag A star. I mean, it's in the direction of Sagittarius. So, that's why they call it that. But the way they proved this, they found they could measure stars really close to it, like only a few, I don't know the actual distance, probably less than a light year away, and they could see how fast they're actually orbiting this black hole. So that's how you figure out the mass of the black hole. You know the mass of those stars, and then you just figure out how long it takes. So one of those stars went all the way around the center of our galaxy in just 15 years. So that's fast. It takes us 250 million years to go around our own.
Wow.
And this is like her favorite star, Andrea Ghez. It's her favorite star in the whole universe because she watched it for 15 years going around the entire center of our galaxy in just 15 years. However, this is not as easy as you think because it's very hard to get the resolution in there. So they have to use all kinds of tricks, which most telescopes can't do. So they use something called adaptive optics, which is the Star Wars technology that a lot of telescopes now have. You shine a laser beam in, then you correct for all the little distortions that our atmosphere creates on the starlight coming in. The air is only 784 times less dense than water. So the air is still fairly dense and distorting. So you have
Yeah.
to correct for that if you don't have like something like a space telescope, which you don't. And then on top of that, they did interferometry with 4 major 8-meter telescopes on the Earth. So they hooked through computers. They hooked 4 giant 8-meter telescopes together to make them work like one telescope, almost similar to the Event Horizon telescope
Right.
where they did 8 radio telescopes to take a picture of the black hole. So they needed so much more resolution to get that fine, within a light year of the center of our galaxy to see what these stars are actually doing. And then, of course, they have a visual. They put it all in motion. They're not all in the same plane. It's really interesting stuff. So this is not as easy as it looks. And probably that's what helped them get the prize, too. All the work and the years and the data,
Yeah.
those other things they had to do to get those tremendously resolved pictures so they can show a little video in 5 minutes. You get a sense of what they spent 20 years doing. But it's neat to see, that power and how those stars go around the galaxy that quickly.
Yeah.
Yeah.
Wow. Well, nice work
Yeah.
to Andrea and to Reinhard. Did they
Right.
work together?
I
Uh,
think, well, probably somewhat. Andrea is also a regular teacher at UCLA. I watch
mm,
some TED Talks and other things by her. I mean, she's really kind of fun. Her students get to do neat things. She has the direct feed to the Keck telescope in Hawaii.
oh,
Like she
nice.
was in the room, they had a video on her, and there were some of her grad students, and she was getting live images from that telescope. in Hawaii, which is, well, distance doesn't matter. You can do remote telescopes. And then they actually go in her class, they actually go to the Mount Palomar telescope in LA,
Nice.
part of her class. So it'd be fun to take in her class. And then Gensel, he's German, so he's little more reserved. He's not as but he teaches at Berkeley and he runs the Max Planck Institute for Extraterrestrial Physics.
Oh,
This guy is also very brilliant, does a lot of, experimental work. But Andrea is just, more fun and just has see, she's a lot more fun than Reinhard. But still, so I'm sure they teamed up. They're not at the same college, but they're not far apart. Berkeley and UCLA, I mean, I haven't been out there, but they're not far apart.
sure, sure. That
Hmm.
must be, that's really lucky to be able to be so close to a telescope like that.
Yeah, yeah,
Because
we
I
don't have
don't
one.
know, yeah, I was gonna say I don't know what the closest one here is, but
Um,
I imagine that there aren't a lot of people who grow up having access to
mm,
large telescopes
yeah,
like that.
right.
Um, well, very cool.
Yeah.
Nice work to both of them.
Oh yeah, and they're still working on these things, obviously, and then I'm sure, as I said, more people will now get in the field. They'll be advisors. I know a Nobel Prize laureate came to our college once a few years ago. Jerry LaSala went to school with him at Yale
Okay.
in medicine, and so he gave us a talk, and I invited all my students, obviously, and I went to see him. And he said he got so busy after that, obviously before COVID, giving live lectures around the world, that he had less time to actually do some of the research.
Yeah.
I forgot his name now, but it was probably 5 years ago in Nobel Prize in Medicine. So I'm sure these people now will have a lot of demands on them. I mean, they're still teachers, but they can probably do what they want now.
Right. 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 Well, very cool. So, I mean, I thought it was you had mentioned Sagittarius A star,
Hmm.
and for our listeners, it's actually spelled Sagittarius A asterisk,
Yeah,
um, but it's you say it as A star, and
yeah.
that's our central kind of black hole at the center of our Milky Way.
Hmm.
And I think most scientists agree or think that supermassive black holes sit at the center of most large galaxies.
Yeah,
Uh,
all of them pretty much now.
mhm.
Just most, yeah.
Yeah. And I think Bernie, you'd also mentioned the Event Horizon Telescope, which
Hmm.
was it's essentially this global network of radio telescopes.
Yeah.
And was it last year that they took a photo of the
Yeah,
end of
April of
the event?
2019. It seems a long time ago now with everything that happened this year, but it was only about a year ago. Yep.
And that was one, I think the photo was, it's basically kind of this blurry image of a dark spot and reddish orange, kind of a ring, and there's like a brighter spot kind of near the bottom of
Yeah,
that ring. Um,
yeah. That's
kind
the
of,
light bending around the galaxy and coming back towards us around the.
yeah,
Yeah.
the accretion disk, is it not?
Hmm. Yeah.
Yeah. Okay. Um, Actually, since I know we were talking about the Event Horizon Telescope,
Hmm.
but I thought you had mentioned that
Hmm.
the Event Horizon isn't actually what we think.
Hmm. It's, oh, that's right. Yeah, it's not like an actual region. You wouldn't even know when you go by this. The Schwarzschild radius, it's called. You wouldn't even know that because it's nothing's actually there. It's kind of a misconception about black holes.
So actually, if we step back a little bit,
Hmm.
the Event Horizon is essentially this,
Hmm.
what do you call it, like a barrier, a
Hmm.
border or something?
Yeah,
About
it's the point of no return.
yeah,
Nothing actually there.
it's about 2 point what radii?
Oh, it depends on the mass of the black hole.
Oh, that's right. That's
In
right.
the case of the supermassive, it's 15 million miles.
Yeah.
And like if you shrunk the Earth down to black hole, it's the size of a marble. It's like 2 centimeters. And if you
Yeah.
take a normal sun, like if you took our sun and turned a black hole, it would be probably about a mile or two across.
And so this event horizon is basically at radii or less than a certain amount, light
Hmm.
will continue, it'll go towards the black hole and it will just be absorbed. And there
Yeah.
will be some point where light is just far enough that it'll just wrap around it and then
Hmm.
come out the other side. And so
Right.
that's what we talk about when we talk about the event horizon.
Hmm.
And I think in general, kind of black hole terms, it's also where like matter kind of breaks up into what not really antimatter. Uh what's the word? Like the I can't think of the word.
And the virtual particles or?
Yeah, the two types of particles.
Yeah. Well, that's how Hawking proved the Hawking radiation. When a
Right,
particle gets right to the event horizon, half will go in and half will go out, so it can't
right.
back out.
Antiparticles and particles, I guess,
Yeah.
is
So a
what I'm
little
trying.
black hole will evaporate
Yep.
quickly, but a big one will be trillions and trillions of years.
And so you were saying that
Mhm.
there's not actually just a specific line, but it's actually
Mhm.
like a space or region.
Yeah. Yeah.
And so we wouldn't even know basically that we had crossed that
Right. You
line.
wouldn't know that you crossed that line, right?
So it's a slow death rather
Yeah.
than a
So, I mean, if
instant.
it's a supermassive one, it could take you like a whole year. If it's a little one, it might take you a few seconds. And intermediate ones, if there are any, might take a few hours or whatever.
Yeah. But as you get closer, the faster you're pulled in, aren't you?
Yeah, right. And the way you get pulled in is this whole process called spaghettification. So that's really interesting too. So, I mean, you can think of it as a human. Obviously, if you could throw something in, you would see this happen to the object. So the reason that happens now, because a black hole is basically pure gravity. So the gravitational energy is overcoming the electromagnetic energy that's keeping your atoms and molecules together. So the difference in gravity between the feet and even your head will be huge, almost like a tidal force. I mean, it is basically a tidal force. It'll be so much of a difference and so much more powerful than the electromagnetic energy that it's just going to start ripping all those molecules apart, eventually down to your very quantum bits.
Yeah.
Yeah,
Sounds like really like a great way to die.
yeah, yeah, it would be. Yeah,
No, it
and
wouldn't.
a great way to go, of course. Well, it wouldn't take long if it's a small enough one.
Right,
If
right.
you go in the one in the center of a galaxy, it would take a whole year. But otherwise, it'd be pretty quick. Pretty quick.
So if you're contemplating,
Yeah, well, we can't jump into one.
yeah,
Yeah,
that's not a good idea.
no.
Although maybe with all the commercial space,
Mhm. All the
space flight
launches now we
options,
can get.
yeah.
Yeah. Well, the nearest one is about still a couple thousand light years away in the constellation of Cygnus. So even at the speed of light, it would take us a couple thousand years to even get to it. So no, we're a long ways off from doing that.
Oh wait, so the one in the center of our galaxy is not the closest one.
Oh no, no, that's 28, 26,000 light years away. We
Oh,
have
okay.
our own. Actually, they found 40,000 similar ones near that, and our galaxy probably has literally millions and millions of black holes.
Oh wow. Okay.
Oh yeah, they're pretty common because that's one of the ways 1%, a little less than 1% of all the stars will die that way,
Yeah.
and all different types of black holes. So yeah,
Oh, like smaller ones, you mean?
yeah, the smaller ones don't go that way. They'll turn into planetary nebula and so on.
Yeah, yeah, yeah.
White
Okay.
dwarfs. Kind of
Gotcha.
enters the exact opposite. You have a black hole and a white dwarf, and
Right, right,
terms they came up with. They're just names, but it's an actual physical process that they're naming in some way that we can understand it.
right.
Yeah,
Makes sense.
yeah.
All right. So, before we leave you today, instead of mass consumerism, think about contributing to mass learningism. Uh, and so I wanted to give a shout out that NASA's Universe of Learning, they are hosting something called Black Holes Out of the Shadows. And this is a conversation that they're hosting with a couple of astronomers, researchers, professors on Thursday, December 3rd at 12:30, and it's virtual. And so they're just going to talk more about black holes and what scientists are into when they study black holes. And so they're going to have Professor Doe uh, will present more on the Nobel Prize winning work. Dr. Kristen Dage will kind of talk about missing black holes,
Hmm.
specifically with intermediate sized black holes. And then Professor Sarah Markoff will talk about the role of black holes in the universe
Hmm.
and some of the open questions that we have about them.
Hmm.
So I just wanted to throw that out there because we do this every year. And I was just telling Bernie before the show that I feel like I'm always like, I don't know anything about black holes.
Well, now you
Versus
do.
Bernie, versus
Now you
Bernie.
do, sir.
Well, when I was doing research, I was like, oh, I remember doing this
Hmm.
research.
Yeah.
So, anyways, for if you're interested, check that out. NASA celebrates Black Hole Friday as well, and we
Or
hope
what time on Thursday the third will this be?
12:30 p.m.
12:30. Okay, good.
Actually, that's Pacific time, so 3:30 p.m. our time.
3:30 for us. Okay.
And I'll
Yep.
share the link on
Mhm.
on the Twitter as well, so you can check that out on your own time.
Yeah.
You have been listening to Scientifically Speaking here on WMPG with myself and Bernie. Stay tuned for Sports Jam with Colin and Connor. And from your favorite nerds, mask up, and we wish you healthy bodies and clean air. I had a question,
Yeah.
and I'm not sure if you know the answer, but
Hmm.
I just thought of it today.
Hmm.
What would happen if, for example, Mercury was no longer in our solar system?
Oh, yeah, good question. See, Mercury is an interesting planet too because its orbit precesses. So it's starting to the sun is obviously not as powerful as a black hole, but as you get near a black hole, your orbit would precess and you would do all these things in much more extreme cases. And Mercury's interesting too because if we were to build a Dyson sphere around the sun, we would need almost as much material as the entire planet Mercury.
Hmm.
We could take Mercury apart and turn it into a sphere and capture all the energy of our sun, which would solve our energy problems for the next billion plus years. Yeah, so that's actually a very good question. Right now, we can't do that. We can do it mathematically, and Freeman Dyson actually had done this 20, 30 years ago.
Yeah.
We would need about that much material. It doesn't have to be a solid sphere. It can be like, it could be space in between, but it would have to capture the energy of the sun, and that's about how much material you would need. Um, but I don't know. You have to do like an environmental research work on what would happen without Mercury there anymore. But I mean, I don't know. If it's not a living planet, you could sacrifice it. You could use it for that. It's, I don't know what
Like,
exactly.
would anything be different for us?
Um, I don't know. I know Neil Coleman's wrote a book about what would happen if the Earth didn't have a moon, or if it had two moons, or if the moon went the other direction. You can do all the physics on this. So I'm sure
Yeah.
you can do the physics on Mercury. I think if you took out Venus, it'd be a big difference because it's more massive, it's closer to us. Mercury's a lot smaller, it's further away from us. Um, I
Or like Mars,
would,
you
would
know.
shift. I mean, I don't know the physics behind it. The orbits would probably shift a little bit.